Okay, so what I want to do today is work out the spectrum of chiral fields in the case of intersecting branes and also deal with anomalies. And then I'm going to take a general perspective about the internal space and get actually, again, geometric topological expressions for the spectrum. So what we have, with this general background that we discussed with the premise by which we want to understand four-dimensional physics, we have turned to D-branes as one framework within which we want to explain particle physics. And just dealing with n-coincident branes, we saw the emergence of non-abelian gauge symmetry that, of course, was associated with gauge bosons in 10 dimensions. And then I argued that if we reduce now this theory, so in principle, if we are now down compactification with D-branes, so if our four-dimensional world, so let me denote it now a little bit more generally in the fibered version, okay, is reduced on down to Minkowski space across compact six-dimensional space. And we are dealing now with the branes. For example, a particular p-brane, its boundary. So, for example, it's p plus one-dimensional word volume, and then in 4 dimensions, it fills up the space, but then in internal space, it wraps a cycle that is p minus 3-dimensional. Okay? So the theory has UN gauge symmetry. We have n branes, and then reduction gave us the scaling that depends on a gauge coupling. With the, in particular, we got the expression, then the gauge coupling was related to the volume of cycle because the actual gauge theory lived on the brane. So this was the dimension of the cycle only, and then the string coupling, the string scale was introduced here, and it goes as 1 over G string because it corresponds to calculation of the kinetic energy for gauge couplings in the open string context. Now, this possibility that now we have actually gauge theories living just on the word volume of the brane, so not filling up this whole internal space, gave us a possibility that we could get relationship between M. Planck and G. Young-Mills to be of the form volume of the transverse internal space transverse to this particular cycle, M string square. So that was actually 9 minus P divided by G string. Okay? So recall we Planck constant we got just from the closed sector calculation of the 10-dimensional Einstein action, and then reducing it down to 4 dimensions gave us scaling relation again. M Planck square came about as M string to the 8, the whole volume of 6-dimensional space divided by G string square, because that the actual term came from calculation of the closed string sector. In any case, that was the formula that one arrived at. Recall that the space of the volume of the transfer space was associated with this is 11 again. So let me put it like that, and m string square. So this is the actual expression that we got, because I mentioned the transfer space was 6 minus p minus 3, which was 9 minus p. Okay. So in the case that we have branes with p smaller than 9, we have non-trivial transverse volume, and now we can tune this transverse volume. We cannot do it in the case when we are dealing only with closed strings, like in the heterotic case, but in this case we have now the opportunity of scaling this transverse volume in such a way that we can still ensure M Planck large, Young-Mills coupling of order 1, keeping G string perturbative. Okay, so this is still perturbative, and then matching that onto 4-dimensional couplings, we now have a new opportunity to deal with the M string, much smaller than M Planck, as long as the volume measured in string radii, okay, was much bigger than 1. Okay, so we can push the whole proposal here now to the case of M string going as low as TV scale. So actually the scale where we expect non-trivial aspects of particle physics, while on the other hand, if we go that low, that indeed, as Tom said, it turns out that in this case, if we take 2 dimensions large, so 2 transverse dimension large in this case, and so 2 of them, so let me say R1 and R2 large, but then the rest 3 through 9 minus p still of order R string. Okay, so just 2 large others, then we can push this R12 down to millimeter scale. And that you can check again. So this is just repeating rather trivial aspects, but it's very key about some new phenomena that do arise because we are now dealing with gauge dynamics arising from the theory on the word volume of branes. Indeed. So those are radii. So basically, the volume is specified by that many dimensions. So basically, we are dealing with that many transverse dimensions from 1, 2 to 9 minus p. Okay, if I take 2 of them to be large compared to string radius, okay, I can push the value of those 2 of them down to millimeter scale.
Why only 2?
Well, if you have all of them, then you cannot, right? So if I'm making the whole transfer space, all directions in transfer space to the brane to be of the same order of magnitude, then I cannot push it down all of them down to
Mirjam,
yes,
we're pointing out that the reason people wanted such large extra dimensions was because you might actually be able to measure them in fifth-fourths.
right,
Type experiment.
like at Stanford.
So they were looking for as big a dimension as they could possibly.
Right, but there was so what if you take only 1, then it becomes much larger, another 17 orders of magnitude larger. But of course, this is excluded experimentally, right? Because we wouldn't measure this effect because extra dimension would be so large, and that would affect our measurements of gravity and all that, right? So this one was actually not excluded, okay? And this is as large than, okay, so this is actually the case when you push it to the range that is not excluded yet, okay? And as large as possible, so with 2 radii. If you have 3, 4, if you have 3 brane, right? If those are 3 branes, then is the whole transverse space is 6-dimensional because the 3 brane is just a point in internal space. Okay, if you push all of them, that would be then all 6 radii of internal volume, right? But then it would scale with some different power, would be much smaller, right? Then, but of course, still much bigger than the TV radius, which is about 10 to the minus 16 centimeters. Okay. All right. So this is just very straightforward, but very intriguing new physics possibility. Okay, they triggered a lot of activities, but that's not so much a core of my discussions, because I would actually now like to continue. Well, maybe I should say one more thing, because we'll use those things. The actual effective theory that arises by looking at excitations, okay, on this word volume of the brain involves gauge fields, okay, whose lowest derivative coupling is just kinetic energy, okay, for this UN gauge symmetry. But actually the whole action is expected to be, so the whole D-brane action is expected to be augmented to the whole Born-Infield action. Okay. And so it lives on the word volume of those branes. So this we denote it as the xi's, and we had p plus 1 of them. And then we one way of writing this whole augmented Born-Infield action would involve now the gauge field strength. So if this is gauge field strength associated with non-abelian gauge symmetry, we also have then additional terms. If one tries to put sort of units in it, there would be also induced metric on the word volume, G mu nu, and actually also induced B field on the word volume. And this induced metric on the word volume will actually be associated with inducing extrascalar fields living on this word volume. So the lowest order term that I pulled out to get out the kinetic energy for gauge fields, we then reduce down to 4 dimensions to get connection to a gauge coupling in 4 dimensions. And here it comes actually with a string tension P. Now, that's the one that was very carefully calculated in an original paper by Polchinski, and it's also explicitly in the book. In any way, this is not actually the only term that is induced in the presence of D-branes. There are also the so-called Wezumino terms. And basically, the leading term in this Wezumino action has to do with the fact that actually this D-brane sources a specific Ramon-Ramon potential. Okay? So it actually couples to the Ramon-Ramon fields of type 2 theory. And in general, this, and there may be some relative minus signs like this. And yeah, I took care of 1 over G string, which is encoded in dilaton. Anyway, the point is the Wezumino action, okay, again, will involve integral of the corresponding Ramon-Ramon form, which in this case is P plus 1 gauge form, P plus 1 form, and that's again integrated over the word volume of the brain. Okay, but that's not the whole story. Actually, we can expand this Wezumino action in all the different forms, because they couple with the induced gauge field on the brain through topological term, the so-called term class, and then this also involves the trace. So formally, it's of the form of the trace like this, over induced gauge fields, actually also B field. Even more, there is also dependence on the corresponding curvature terms, induced metric, the so-called roof genus. So this is some specific polynomial expressed in terms of the curvature induced on the brain. The reason in general, we are writing that formally in this way. Okay. And so the first term is, I want to remind you that the first term would be Cp plus 1. And the next term, if I forget about issues of induced curvature, if I'm focusing only on gauge degrees of freedom, we see that the next term would come in the form of the form Cp minus 1, wedge trace of F. And the next one, if it's still there, if we have enough forms, Cp minus 3, wedge trace Fa, wedge Fa. So this is basically Fa specifies specific non-abelian gauge symmetry, gauge dynamics on the brain. Okay? The reason I'm putting those terms down is they will be very important in canceling anomalies in such theories as we go down to 4 dimensions. So let's keep this in mind. And now let's turn to the more to the next stage, trying to get the next set of spectra, which would be now associated with the space-time chiral fermions. Okay? And so how we obtain space-time chiral fermion. And again, that's the reason why in this case I'm going to turn to D6 branes, because will be the setup, the framework in which I'll geometrically deduce for you the appearance of chiral matter in 4 dimensions. So as questions were raised in the first lecture, this is one specific setup. Okay, it's type 2A, and it's only with specific D-branes. Okay, but it gives us the key features of getting chiral matter in those in such frameworks. Okay, now other type 2A pictures or dualities to type 2B or type 1 will actually involve certain dualities that will change the intersection of these original branes to other type of branes with some fluxes on top of them. And their fluxes, magnetic fluxes on those branes, will induce chirality. Okay? So it's somewhat less geometric, but through T-duality, very straightforward way. So let me stick to this geometric picture and go on and argue about the appearance of chiral matter in this context. All right. So I want to argue, so chiral matter. And now for this purpose, I'm going to focus on specific branes, which are D6 branes. Okay? And trying to address what is happening in internal space when I have different sets of D6 branes wrapping internal cycles. So let me just focus on this internal space, 6-dimensional. Okay, and because I'm starting with D6 branes, in this internal space, D6 branes will wrap some 3 cycle. So let me just denote that by pi cycle pi, and pi is actually 3 cycle. So it's a 3-dimensional submanifold of this original one without any boundaries. Okay? So this would be if I have one set of branes, and let me call those branes A. So again, in ordinary space, they just fill out our space. Okay? So we have a set of D6 branes. Let me choose NA of them. That will wrap an internal cycle. Okay? Now I can choose another set of branes which can wrap some other 3 cycle in this internal space. So if we have some other set of branes, they will wrap some other cycle, pi b, 3 cycle, and let me take NB of them. Okay. As far as gauge theory, gauge bosons go in this context, we know that what we are going to obtain in terms of massless spectrum that comes from quantizing branes, open strings that start and end on the same brane, would be the gauge symmetry. One associated with NA branes, wrapping one cycle, and another one associated with NB branes, wrapping another cycle. So in 4 dimensions, we expect this gauge symmetry to appear. Just basically from original quantization of open strings that start and end on the same set of branes. Yes?
We would like the 3 cycles to be of non-trivial homology.
Yes. Right, of course. I don't want them to disappear, right? So I want the manifold that has non-trivial cycles in homology.
But could we not have stable cycles? I mean, in
Right.
If they move a little bit, they will increase energy, but still offer trivial homology.
Well, the point is that so the point is, if cycles were rigid, okay, then I wouldn't have any moduli associated with the formation of those cycles in certain homology class. Okay. This is not generically the case.
So you would like flat directions, but still of non-trivial because.
Yeah, of course. I don't like flat directions because that brings me back to moduli stabilization issue. I want to deal with as few of them as possible, okay, and so on, possibility. But anyway, I'm allowing, first of all, that homology associated with this is non-trivial, right? But whether, I have rigid cycles in this specific would be preferred, okay? So basically what we are now dealing with 2 sets of 3 cycles that intersect in 6-dimensional space. And generically, such cycles would intersect at finite number of points, unless I have some very degenerate thing that, So generically, two, 3 cycles intersect at a number of points. So codimension 6, right, in internal space, in M6. Okay. And actually, this number of intersections is a topological number. Okay, it's a number that we can actually calculate just based on homology analysis of cycles in particular space. Okay, and it's not independent. It's independent of specific metric. Okay, and so a natural way is to parameterize a cycle. Let me discuss a 3 cycle, and again, it's a non-trivial 3 cycle, and I'm going to basically always focus just on homology description. So I can parameterize any 3 cycle in terms of what we call integer basis of cycles, and they are actually in 6-dimensional space. I can choose a basis of 3 cycles, and actually their number goes if it's a Kähler space or if it's Calabi-Yau, it's specified by the number of, so it goes from 1 to number of the specific Betti number plus 1. Okay, so we can classify the number of 3 cycles, non-trivial 3 cycles, and 1 is just the holomorphic 3 cycle, and the rest are 2,1 cycles associated with specific deformations. So the set of cycles, so any cycle can be specified in terms of integers times the choice of canonical cycles and their dual ones. And dual ones I'm going to denote with Bj. Okay? And also with the number of integers. Okay? So the set of cycles, 3 cycle A, I. So I and J both run from 1 to a Betti number 2, 1 plus 1. Okay. So both of them. So we have twice that many cycles, original and the dual ones. And there is a notion of a product in homology of those cycles with the property that the product of those cycles is always 0 unless the original and the dual one are the same. And also has the property that it's antisymmetric. So if I do it in the reverse order as a product, it changes sign. Okay. So this prescription is basically generalization of a cross product of vectors in ordinary space. Okay. And that's now introduced. So with introduction of such basis of cycles, we can now define the product in homology of 2 cycles, expanding in terms of such integer bases. So n and m's are actually co-prime number, integer valued co-prime numbers. So in any way, using this prescription, this product, this expansion of its cycles in terms of this n and m wrapping numbers with the definition of the product, we get the expression that such a product is equal to NAI MBJ minus MAJ NBI. Yeah? So giving it a set of such integer valued description of cycles in terms of this integer value basis, we can express really such a number of intersections just in terms of those wrapping numbers n and m. Okay. The simplest case is to really look at the simplest 6-dimensional compact space, which would be 6 torus. Okay. And I'm going to be even simpler, namely I can choose a torus to 6 torus. So this is the simplest way of describing particular compact space. So in this case, this would be, I would write it as a direct product of 2 tori. So I would take direct product of 3 2 tori. Now, each of, coordinates of single 2 torus will live on a compact space. Okay. If this is a particular lattice translation in one direction and this is lattice translation along another direction, we identify those points, and that would be one particular description of a compact 2 torus. Okay. Yes? Yes, thank you. Yeah, why did I do that? Thank you. Of course, because of this. Of course, yeah. So if I want this indices, it's actually a little awkward to do upper-lower indices here, but anyway, so this is J, or let me do it I. Okay, in any case, indeed, this is an analog of this intersection number. So let me look at the specific example. So I'm going to take one torus, specify, with this particular lattice, and now another 2-dimensional torus, and let me just draw it in some similar case of very special lattice. Okay. So again, if I identify this point with this and this with this, I get this famous donut. Okay, but I'm unfolding it, keeping in mind that those ends are identified. Okay. So now the basis of cycles in this case, the basis of cycles can be actually written 3 cycles. The simplest example is the case when I have the product of 1 cycle. So 3 cycle on 6 torus is written as a product of 1 cycles on each of the 3 tori. So this would be, so let me just write 3 cycle will be now written as a 1 cycle on first torus times 1 cycle on the second torus times 1 cycles on the third torus. Okay? So 3 cycles product of 1 cycles on each of the 2 torus. And then the natural basis, integer basis of cycles on torus is basically cycle A. So this would be, let me call it now instead of capital A, this would be 1 cycle A1 for the first torus, and the second cycle would be B1. So this is B1. And similarly for the other guys. Okay? So the basis of cycles, of 3 cycles, is basically basis of products of, let's say, A1 with A2 with A3. And then similarly A1 with B2 with B3. And 2 more options with 2 Bs. Okay? Those are analogs of cycles AI. 3 cycles AI. Okay? Now similarly, oops, this is not good. So similarly, so since I have this, let me just draw now the basis for BJs. Similarly, I can do that now for the BJs and get, so the dual cycles, BJs, would be specified as does 1B. So this would be B1 with A2 with A3, and then do, and the last one would be B1. So let me do it. So plus permutations, 3 permutations, and the last one would be B1, B2, B3. I think, so anyway, let me just, okay. The point is I can do that, the dual basis in terms of Bs, with B2, with B3, and then just 1. So in this case, to really make it dual, this would be B1 with A2 with A3, and 2 more permutations. Okay? Yeah?
How do you choose small a's and b's to make a large A and B
So,
Can you explain that again?
yeah, so the point is, you see, I want to reproduce something I just erased, that the intersection, right, of cycle A and B is orthonormal, right? And so let me just, this basis of 1 cycles on each torus have automatically the property that each 1 cycle AI with cycle intersection with the cycle BJ, okay? So AI with BJ actually will never intersect unless they are equal. Okay? So in each 2 torus, the basis of cycles is the natural orthonormal, has natural orthonormal, and now you see that actually I'm reproducing.
So let's say you say that A1 cos A2 cos A3 is orthogonal to.
Yeah. So this and this intersect exactly once, right? And you see 2 with 2 will do that, but all the other cross products are 0. And of course, we also keep in mind that A with A is always 0 and B with B, right? This is automatic. Okay, because they don't intersect in the sense of cross product, okay? So this is like a natural simple basis, okay, of A and B cycles. Now for the torus, and now we can write the actual intersection number by expanding the general 3 cycle in the basis of those A cycles and B cycles, where these integer numbers are now specified by wrapping numbers depending which A cycles we have and which B cycles we have. So in other ways, I can now write the actual expansion of any 3 cycles onto torus in terms of product of expansion of one cycles. That would mean integer numbers. Let me call them now n, 1, a1. Now I'll suppress upper lower indices, plus m1, b1. So those are integer numbers associated with what linear combination of one cycles on first torus we take, cross taking, so n2, a2 plus m2, b2, and the same for 3. Okay? So in the basis of one cycles, the general 3 cycle onto torus will be now written as the product of one cycles on each torus, which we expand now in this integer basis of one cycles in each torus. Okay? Using our relationship about the intersection product of cycles, then it's very easy to see that if we intersect now on this 6 torus, 3 cycle, 1 3 cycle with certain wrapping number, NIA and MIA, with another cycle with wrapping number NIB and MIB, we get this intersection number to be now product of N1A with M1B minus M1A with N1B. This is for first cycle. We can do it for second and third. So it's a product from 1 to 3. Okay. Again, this is just an integer number, just depending on the choice of the wrapping numbers. Is that clear? Yes?
Is there a reason why you don't consider 3 cycles that are products of an entire T2?
Yes, one could consider that. And one can consider more general to torus. This is the simplest case, okay? But the idea is general, and it's encoded in this context, okay? So with the physicist, explanation of how to introduce the intersection product of cycles, okay, by choosing this orthonormal integer base of 3 cycles, okay, we can really see that this number is just some integer number that depends on only wrapping numbers, only on wrapping numbers n and m, okay? And so in any compact space with well, most of the time those will be Calabi-Yau spaces because we want supersymmetry in lower dimensions. So in all those cases, the number of intersection points is just this topological number. Okay? So, yeah.
The question was about the cycle containing one T2 itself, right?
Yeah.
Right.
So if this is a canonical basis, we should be able to express that cycle as well using this basis.
Right.
How would we write that cycle?
No, that's not necessary cycle.
No, T2 times a circle in another T2.
Well, I can use T-duality, okay? Let me just yeah.
Using this basis, we should be able to write that T2 times a circle in
Mm-hmm.
another T2, right?
I think this is a complete basis.
It is complete or incomplete?
This basis has 8 dimensions. I think if you choose 3 cycles from the total of 6 cycles, you get 20 different choices.
So,
So we are not working with a complete basis.
well, I just showed you an example, right? I didn't show you with I show an example of parameterizing 3 cycles in terms of 1 cycles, okay? So it's a special subset of bases, right? Okay? But as far as 1 cycle representations in each 2 torus, that is the complete basis. A and B are exactly the 2, okay? 1 cycles that span the whole basis. So, but it is a special, choice. Okay. So within the subset of 3 cycles, representing in terms strictly of 1 cycles, this is the actual intersection numbers among them. So it's a subclass. Okay. But one can think about it in more general terms, of course. And yeah, I think your concern was that I don't have the complete basis, and so am I getting the right thing? But they close onto themselves, so product of one cycles. As long as each of the one cycles is in a complete basis, it's fine. Okay? All right, so this is in area. The reason I'm emphasizing that is that actually the number of this intersection is a specific number, and it's a topological number. Okay? Now I'm going to turn, yes?
So how are these small n's and m's related to the big n?
Right, I mean, so basically, you see, I'm splitting that in a product, okay? So I think the one way of writing that, NAs, okay, will be with the vector of 3 integers, because I went into, writing the, 3 cycles in terms of 1 cycles. Okay, so let me not go into it, but it's straightforward, right? Once I wrote it like this, you can see the map onto my basis. Okay? Anyway, so this is the key point, and it's really generic property. Okay? Sorry?
One should be able to write some integer coefficients, not a vector, but some
Right, those are the integer coefficients, right?
in front of the cycle, like this big N.
Yeah, so this big N, okay?
Should be a vector, should be a number.
So, yes, it is, right? If I write that as, let me write, just bear with me. If N1, N2, N3, okay, will be the, so it's this product, okay? I could split those things into positive values things, and then the other one, I can convince myself that would be in this way written, yeah. It becomes a product of n's and m's, okay? So I think it would look like something, it's straightforward map, okay? It's straightforward map because I can write this, the cycle like this, and each of this in that basis. It's straightforward which combination will make this product and which, well, let me not, this is a thing that is straightforward to derive. But it's not so much the point. The point is that we can calculate in principle this integer numbers, okay? So now the next thing that I want to focus is what happens at those intersections, okay?
Are the cycles oriented or unoriented?
I'm not doing projection yet, so they are oriented, okay? So it is really orientation that I'm choosing. Okay, because I'm not doing orienting for projection yet. Okay, so in any case, so what I want to do now is I want to look at this. I want to look at this particular intersection. Okay. Now at each intersection like that, locally, I can describe the intersection of 2-3 cycles, basically in flat space. Again, I can write this, so intersection of 2-3 cycles. So let me take magnifying glass, okay, and look at this blown up region by which I describe this particular intersection. So let this be A cycle and this be B cycle, 3 cycle. Okay. So locally, this is R6 space in which 3 cycles intersect. And again, I can use the local description by writing each of these 3 cycles as 1 cycles locally, okay, in R2. Okay, so local description of such intersection can be described as intersections of 1 cycles, 3 1 cycles. Okay, so if I take one R2, another one, and the third one. Okay, so I can take 1 cycle, and let me denote it, okay, as just a line, particular line in this R2 space as a local thing. Okay, and another one again as a one cycle. Okay? So it's a local description in each of the R2. I can view that as some one cycles, okay, that intersect at some angle, which I'm going to parameterize as pi theta. Okay? And similarly, the second one, and the third one. Like this, okay? And so the actual angle here, I'm going to denote at each of the R2. This would be pi theta 2, and this would be pi theta 3. But just for specific case, I chose this would be the negative angle because now, because of this orientation issue, if those are the directions, this is now associated with the, so let me, if I'm having orientation here, that would be the direction of one cycle chosen for specific case. Okay? So basically, locally, I can describe this as really just intersections in flat space of a product of one cycles. Okay? And I want to quantize string in this background. Okay? So locally, this is flat target space. Okay? So the string theory itself, of course, this is internal space. We always have our R3,1, right, as well. But this stuff lives on top of each other. Okay. All right. So this is the local description at this intersection. Basically, it's flat. So we are dealing with free string theory in flat target space. Okay. So basically, what we have to quantize is possibly new string states that appear by quantizing free string, okay, but with new boundary conditions. Okay. And the boundary conditions that I'm going to deal with will be strings that start on one brane and end on another. Okay? So I have now open strings basically stretching near each intersection between the two sets of branes. Okay? So what it is, it's free string theory, but where I'm imposing the corresponding Dirichlet-Neumann boundary conditions in a non-trivial way. Recall, when we quantize string that starts and ends on the same brane, we did something like this. But now we start strings starting on one brane and ending on another. And so boundary conditions are non-trivial. All right? So let's work out those boundary conditions. Okay. So just like we did boundary conditions for open string that starts on and on the same brane, now we have strings that start on one brane, let's say on brane A, and ends on brane B. And so those are straightforward. This is just simple, flat. So it's free string theory. Superstring, open superstring with non-trivial boundary conditions. Okay, so let me continue with that and quantize it and argue about the spectrum when we quantize such open string. So basically, it's really still free string theory. And so what we have is, let me parameterize this two-dimensional R2 space in terms of complex coordinate, okay, which I'm going to call capital Z1, capital Z2, capital Z3. Okay. Again, Z1 would be X1 plus I, Y1, and so on. Okay? So this is locally R2. And so I have now boundary conditions. When target space coordinate is here. The string that ends here, okay, has actually on this space Neumann boundary conditions. Okay? And in a transverse direction on this end, it has Dirichlet. Now when the string is on that boundary, along this direction Neumann, along this Dirichlet. Straightforward, we can work this out and get the conditions that, so let me do that. So I have the sigma xi is, this is the Neumann, Neumann boundary condition, and x, so can I, apologies because I have different notation. Let me write this zi as x. Zi is x 2I minus 1 plus I x 2I. And I goes from 1 to 3, and x's go from 1 to 6. Okay, this is just the split. And so it's straightforward to get boundary conditions that 2I minus 1, and then we have Dirichlet condition on x2. This is when sigma equals 0. Okay, clearly, as I argued. Now we have to do boundary conditions on the other end. Okay, and on the other end, it is the sigma on 2I minus 1. Now we have to go along the direction of the second brane, and that's tilted. So this can be written as tangent pi theta I. And then, again, Neumann on x to I equals 0. So this is when sigma is pi, bullshit coordinate is pi. And so those are Dirichlet and, Neumann and Dirichlet come analogously as 2I minus tangent pi theta I x to I minus 1 equals 0. Okay? Well, that's, if I combine those things in this combination, this allows us to quantize string theory precisely, just with these boundary conditions. The upshot is because boundary conditions now involve this tilted direction, okay, will involve actually expansion in terms of oscillator modes that are non-integer modied, okay, but are modied by the value of this angle. So the upshot of satisfying this boundary condition is expansion of quantized string now in terms of z coordinate that can be written in this form. So this is possible to quantize that, and now this has two sets of modes.
The third one is that sigma equals to pi.
Sorry?
Third equation is that sigma equals to pi, right?
Yes, sorry, this is sigma, yes, of course. That was easy to do, right? But here I had to split, indeed. Pi, this is on the second end, indeed. And so satisfying that you can do in terms of worldsheet coordinates. So let me go to Euclidean space, define small worldsheet coordinate z as e to the I. So it's Euclidean time, worldsheet time plus minus I sigma. Okay, so standard thing. And with the bar, analogously, we are on the upper half because it's open string, so imaginary of z is bigger than 0. Okay? So using this worldsheet coordinate description, quantizing now free string theory with this boundary condition produces mode expansion of that type. So it's non-integer modded. So we are modding now over. So what we have now is basically the mode expansion that is non-integer modded. That involves worldsheet z coordinate to minus plus theta I. And then we have another one that involves z bar. So now that I have this, I can erase it and get the actual result. This is now another set of oscillation modes. This is n plus theta I z bar. Those are worldsheet coordinates. And, minus n minus theta I divided by n plus theta I, where n goes over integers. And the ground state of the theory is annihilated by all those modes with n bigger than 0, and here also the positive value. Here starts actually with n0 and higher. So in other ways, on the ground state, so this new ground state is annihilated by these guys. With n bigger than 0, and for the tildes. I'm keeping this empty because this is not the normal ground state. It's actually twisted ground state of the theory. Okay. So basically, this is explicit expansion of the bosonic sector. We have superstring, so we can analogously expand the actual worldsheet Neveu-Schwarz fermion, worldsheet fermions, taking complexified notation, which is suitable also for what we call bosonization, that allows us, so writing this in terms of original, for each of the internal coordinates, we get 2i minus 1 plus I psi 2i. So we can similarly now expand these worldsheet bosons, fermions, with analogous boundary conditions. It's just that now we have two sectors. One is Neveu-Schwarz sector. Okay, so we have certain conditions associated with the Neveu-Schwarz sector and certain conditions associated with the Ramond sector. And so together with this analogous boundary conditions on each end, right, we get expansion again in non-integer modding. So this can be now modded in terms of non-integer modes. So theta, so this is, and let me call that R minus theta I z to the minus R minus a half plus theta I. So this is for, so that would now correspond to R is either half integer, so this is either m plus a half for Neveu-Schwarz sector, and for Ramond, this R that I chose goes over integer. Okay. So we have both non-integer modded modes associated with bosonic and fermionic coordinates, both in Neveu-Schwarz and Ramond sector. Okay. So now we can basically calculate what are the lowest energy excitations. Okay?
Question?
Yes.
Why did you put the pi, or like define your angles with the pi along with them?
It's convention, so I don't carry it around. Yeah, because pi actually disappears. Yeah. Okay. Any other questions?
What is the commutation relation between alpha m and alpha m?
Yeah, there is certain. Fortunately, I don't have this with me, but it's a specific connection within them. Okay. By the way, you can check this in the appendix. This was done quite carefully in the appendix with Richter. In 2003. Okay. And also to identify physical lowest energy excitations and all that, because it's highly non-trivial. I just wanted to give you a flavor, okay? And I'll make a mistake if I work out the corresponding commutation and anti-commutation relations. Yeah.
But what is the name of algebra? Is there any name for this commutation algebra?
Well, it's analogous to Virasoro, right? It is. It's still conformal field theory. right? So it's just that the moding is not by integers, but shifted. Basically, what we are dealing is with the theory that has a new type of ground state, okay, where both bosons and fermions have non-trivial boundary conditions. This is the so-called twisted vacuum of the theory, okay? It's a new set of states that appear associated with the twisted vacuum. Another key thing is that in this quantization actually does not allow for any momentum, okay, in internal space.
But this is technically speaking not twisted, right? Like this, in general, when we talk about twisted states, it's basically we are talking about closed strings.
Yeah.
We are basically dealing with open strings.
Yeah, but we still have the notion of, right?
Modding.
Yeah. So this is actually, yeah, indeed. So another thing is, also there's no momentum. Okay, so in internal space, these modes per se that we quantize are stuck, typically are stuck at this intersection. So this quantization, because there's no momentum, so those are stay stuck. Okay, so with all this, let me just sketch, okay, the actual result for the calculation of of lowest lying energy states in this new type of twisted vacuum. Okay? Anyway. Yes? Yes. Oh, it's 03. Yeah, yeah. I'm sorry. With Papadimitriou was in 03. Okay, but this was an incremental work. There we did Yukawa coupling calculation. Anyway, Kirby, thank you. Thank you. It's 06, but I think I mentioned that at the beginning. Anyway. This is it, okay? So anyway, so let me go on and talk about now actually the states in the Neveu-Schwarz sector, okay, and the states in the Ramon sector, okay? So what we have is, so with this observation of having states that are non-integer modic, we see that as far as the bosonic vacuum, okay, we have non-trivial boundary conditional bosonic states. And actually it's what we would call twisted bosonic vacuum, which I'm going to denote with the sigma, which is actually conformal field in principle associated with it that out of untwisted pure vacuum creates now the twisted vacuum. Okay? And the property of bosonic coordinates, for example, around this vacuum, okay? So for each of the complex direction, okay, we have this twisted vacuum. What it will do, it will create some excited states in this twisted vacuum with the right pole structure that will be compatible with these boundary conditions. And so in particular, you would get on the, its dependence on the worldsheet coordinates will be of the structure like that, -1 minus theta I, which is exactly obtained by acting with alpha -1. Sorry. Let me just. So it is obtained with this guy plus theta I. Okay. So that would be actually the non-trivial state, first excited state, the lowest lying state, the theory. And basically, it's the state that it's a vacuum, bosonic twisted vacuum, okay, which I can't easily describe in terms of bosonic coordinates. It's really a new conformal field in the theory. Okay? And on the other hand, as far as embedding twisted boundary condition on fermions that we had, we actually can write this effect directly using bosonized picture. Okay? So recall that when we have just ordinary Neveu-Schwarz boundary conditions, this fermionic fields in the Neveu-Schwarz sector can be written in terms of bosonized free bosons in the structure like this. And the Neveu-Schwarz and the Ramon sector, which are now Ramon conditions, right, will create for us spin states, vacuum that ensures those boundary conditions. And so we are dealing with the spin states of the type e to the I 1/2 hi. And that ensures proper Ramon boundary conditions on the fermions. Okay. Now we have on top of that, right, this half integer and in this case, integer and half integer modified states, right? In ordinary free string theory, we have now additional twisted boundary conditions. So what will happen now in our context, the fermionic sector will be now represented in bosonized version through shifts of that type. It's subtler, but basically they're shifts of the type. And the Ramon sector will be represented with shifts of the type theta I plus 1/2. Okay? So those are these non-trivial twisted boundary conditions. So actually, as far as fermionic sector of the theory, both Neveu-Schwarz and Ramon can be directly represented in terms of explicit conformal fields of those bosons, which are free bosons, okay? So those are for those that are familiar with some aspects of conformal field theory. So in any case, we expect now to calculate the energy, physical states, physical excitations, okay, by properly finding the physical vertex operators and determining their mass, okay? So if you bear with me, I'll state the results for you. Okay? Here I argued that I basically have to introduce twisted vacuum. So when I'm creating bosonic degrees of freedom, I need this twist field. Okay? But fermions, I can rewrite basically back just in terms of free fermion, but now modded by this non-integer angles. Yeah.
The vacuum that you mentioned is associated with the bosonic coordinate? So
Yes. Yeah. Yes, everything is locally factorized, indeed.
And in general, the theta equals 0 limit is going to be degenerate? Or it's
theta equals 0, yeah, you have to be careful what happens there, because then you start having those strings coming, branes coming on top of each other, okay? And this can be studied carefully, okay? I really, due to lack of time and because I'm not here to teach you conformal field theory, there are issues of that type, and one has to be careful. Yes, you have to be careful. Which modes are there really that we are exciting with what sign of thetas? Okay, and so in the original, so let me maybe state the concrete answer. Okay, that was carefully worked out, and for the lightest lying state, so lowest energy physical states. Okay. So in the Neveu-Schwarz sector, we get bosons, space-time bosons. In the Ramon sector, we'll get space-time fermions. Okay? And so as far as energy level of the Neveu-Schwarz bosons goes, the mass level, so if I calculate the lowest lying mass level of bosons, with my convention that I chose, was convention that I took angle theta 1 and 2. Theta 1 and 2 to be between 1 and 0. I took the blue brane at the bottom right there. And theta 3, a specific convention. I can work this out for any other convention, but let me just to be concrete. In this case, this would be smaller than 0, but bigger than -1. Okay? With this convention of relative angles, okay, the lowest lying energy state will have the 0 mass, will have the mass that is equal to 1/2 theta 1 plus theta 2 plus theta 3. And in the Ramon sector, miraculously, what happens? The lowest lying energy state has 0 mass. Okay? So this is the miracle. So, I mean, this is just telling you results. But I can, with this preliminaries about how to write twisted sector, both in the bosonic sector and in the fermionic sector, I can write explicitly vertex operator for this physical state. So let me write them for this specific case. So basically, for the bosons, I have to excite with bosonic degrees of freedom on a vacuum. It's a twisted vacuum. So I'm going to introduce this twist fields, bosonic twist fields, sigma theta I. Okay. Along with them, I'm going to have Navier-Schwarz fermions, also with twisted boundary conditions, which will come as e to the I theta I hi. And this is the case when this angle is chosen positive, so this would be for first two. I'm writing vertex operator here for physical state. Okay. As far as the third one goes, because it's negative, then you have to be careful. It's related to this issue that was raised about, what it comes with plus theta I or minus theta I, the physical excitation. And so this can be now written in terms of spin field, bosonic twist field as 1 plus theta 3. And then this now comes with e to the I 1 plus, this is i's theta 3 h3. Okay? So this is Navier-Schwarz sector, okay, describing the vertex operator for physical states in internal space. So they are bosonic twist fields, just the twisted vacuum, those that create out of untwisted vacuum, twisted, and then those are the Navier-Schwarz fermions that accompany. Now I also have space-time structure. Okay? In space-time, I can bosonize fermions, and this would just be nothing. Okay? And if I'm in the particular picture of superconformal ghost -1, this would be the vertex operator for boson. The only thing I still have to accompany is with the 4-dimensional momentum, because in the 4-dimension of momentum I have just completely free string, and so this is moving in 4 dimensions freely. As far as internal space goes, it's associated with the states. Yes?
Why are we single out one of the angles?
I chose a particular case. I can, if I have, there is a reason, okay? But this can be, all right? How about for this state? For this state, those are now Navier-Schwarz fermions. In this case, I'm in the Ramon sector, so fermions are Ramon's fermions. I still have ordinary bosonic twist fields for the lowest lying state. But now I have to accompany them with the Ramon fermions, and those are now half integer valued. And so this would now actually involve I theta I with minus a half hi over first two guys. And then this guy is a little tricky, so this is e to the I theta 3 plus a half h3. So this is in internal space. Okay. Now, in ordinary space, those are Ramon fermions, which are in spin representation, and so those would be space-time spinors with, let me call spin fields as alpha, okay, accompanied now with a spinor tensor. This is now describing space-time tensor degrees of freedom of a spinor, and in the canonical picture that has ghost number minus a half, this would be the corresponding vertex operator for space-time fermions. And it also moves in ordinary space. Okay? So as alpha in this case, in terms of bosonized fermions in the 4 dimensions. This I think is of the structure plus. Let me call those bosonized things in ordinary bosons script H1 and script H2. They come with 1/2. 1/2. This is one choice of spinor, and the other one is this. Okay, and GSO projection makes it left-handed fermions. Okay, so this is a spinor, Bose spinor tensor. Okay, for left-handed fermion. Okay, all right. So now we are basically yes. Supersymmetric, that's where I'm getting. Okay, so that is slower than I thought. Anyway, I'm getting to that in a second. Okay, so you see, what I have chosen is actually arbitrary angles, right? So let me just do one simple thing. Those who know some conformal field theory, okay, let me just use the actual expressions for conformal dimensions, work out the actual conformal dimension of this vertex operator, because that will directly tell us at what mass level it appears. Okay? So let me just use the, it's possible to derive actually that for this bosonic twist field, so theta I, its conformal dimension is theta I 1 minus theta I over 2. Again, for bosons, so for any bosons associated with fermions, so AI, this is conformal dimension of this guy's, of course, this factor square over 2. So with this, we are done, except for the only other thing we still have to know is what is conformal dimension of superconformal goes. So e to the a phi has an unusual conformal dimension, which is minus a times a plus 2 over 2. Let me check that I'm writing this correctly. So this is now, yes. Yeah, I think this is all. Now we can work this out. So let's calculate the conformal weight, okay, the conformal dimension of the boson state. So let me just focus on that part, because depending, if the conformal dimension of this term is bigger than 1, this would correspond to massive state, because that would then compensate by giving me positive mass for the momentum square. Okay? If it's smaller, then it's negative mass square. And if it's 1, then it's exactly massless. Okay? So conformal dimensions of, conformal dimension of, so where are we now? Of just bare part without momentum of this guy, working this out, that will give you precisely the answer. You can now work this out. It's just algebra. This gives you 1/2, the standard thing, shifting the vacuum by 1/2 here. And then this sector will give us a bunch of things. A lot of thetas will cancel because of, you see, these are theta squares. For example, those are theta square over 2, and then each twist field gives me minus theta square. So there's actual cancellation. There's only linear dependence on angles. So this is sum of theta i's, and turns out to be over all of them with this convention with 1/2. And then there is another 1/2 left. So this is plus 1/2. All right, so this is the conformal dimension of the core part of the boson, and conformal dimension of the fermion. The core part turns out to be exactly 1. You can convince yourself that with this 1/2, and with that, this precisely gives you the state with conformal dimension 1, independent of the angle. Okay? So we can now translate basically the mass level of this physical fermion is at mass level 0, because its core conformal dimension of the vertex is 1. Okay? For this guy, it depends. If the sum of those guys is bigger than 0, then it will be massive. If it's 0, it will be massless. And if it's smaller than 0, it will be tachyonic. Okay? So let's turn to this analysis, okay? Since I don't want to go over, we have the following conclusion, okay? At each intersection, we encountered twisted sector string theory, where physical massless excitation is massless fermions, massless space-time fermion. Okay? And a boson whose mass depends whether these three angles add up to 0, whether they're bigger than 0 or smaller than 0. Okay? And a boson with a mass equal to 1/2 theta 1 plus theta 2 plus theta 3. Okay? That brings me now to your question. Okay? When the sum of those angles add up to 0, okay? So basically when those angles are SU3 rotation, so angles of cycle of the first brane relative to the second brane is within SU3 rotation, okay? That the sum is 0, we will always get an additional massless fermion, a boson. So along with this fermion that is always massless, no matter how branes intersect, there is now a boson that for special angle becomes massless. Okay? So when those angles are 0, this becomes Carl supermultiplet. Okay? So supersymmetry is recovered in this case. And this is actually the case of what we call special Lagrangians that have the property that the killiform pullback is 0 on the cycles, and also that the holomorphic three-form pullback, imaginary part of it, on the cycle is also 0. So, and it can be precisely locally quantified with the condition that the sum of those angles is 0. So the sum of the angles has to be in the subset of SU3 rotation, not unrelated to SU3 holonomy, okay, that we see in closed sector theory and Calabi-Yau, okay? So I can quantify that better, but I really don't have the time. It's in our review, the way we, in one-to-one correspondence, show that when these angles are 0, cycles read by branes are special Lagrangians. Okay, they are actually supersymmetric cycles, and in this case, the spectrum is the spectrum at each intersection of massless spin 1/2 fermion and the massless boson. All right? So now we basically have the whole spectrum of the theory. Okay? We have gauge symmetry. We have at each intersection massless fermions, where there is supersymmetry, Carl superfield. What is its representation in terms of U and A and U and B? Bifundamental, because string starts on 1. So this is in the representation A, B. So we have Carl fermions appear at each intersection in bifundamental representation like quarks. Okay? And the third thing that we derived at the beginning of this lecture is how many of them do we have? Intersection number. Its intersection number of cycles, again, is a topological number. So it's the second property of standard model that we have, chiral matter at each intersection. And so this is the third property is that the replication is just number of intersection. Family replication is just number of intersections. Okay? So we see that, with intersecting branes, actually on general grounds, we get these key features of the standard model: non-abelian gauge symmetry, chiral matter, and family replication, really in this geometric way. Okay? I have to say, I don't have a good way of explaining why these fermions are massless unless I go into hardcore conformal field theory analysis. Okay? But it's exact. states is precise and exact conformal field theory of free string theory, just with twisted boundary conditions. Okay? And so those are really core general statements about properties of the spectrum in the theory with intersecting branes. So I'm about more than half a lecture behind. In the next lecture, I'll turn to global conditions. Hopefully, I'll do it faster. Okay, and then in the some examples, maybe like I did for torus here, just calculating intersection numbers, and then in the fourth lecture, we'll start dealing with non-perturbative effects in these backgrounds. Yes.
Is this method is fermion due to some spontaneous possibility breaking?
Fermion? So Goldsteiner, you mean maybe?
Is it protected?
Yeah. I don't have the answer to that. No, I don't have the answer to that. Yeah, there could be some index theorem or something that by which I could argue. Well, there would be massless states. But frankly, I tried hard, okay, because this stuff is around now for a long time, right? And yet, the only thing I can show you is like this, right? That it's really strictly massless, right? Is by it's not broken no, the cycles, if they are BPS, they break supersymmetry, right? Branes break if they are BPS branes. But now, I don't think it's a Goldsteiner of broken supersymmetry. I don't think so.
There is no supersymmetry at all?
Well, unless angles add up to 0. Unless you see cycle, you remember the way I choose one brane is along one direction, and then angles of the second brane relative to the first one was such. Okay? So relative supersymmetry has to be preserved. Okay? If the sum of angles is 0,
okay.
Yeah. Basically, it's I have the first brane, and the second one is SU3 rotation relative to the second one. Okay.
So if let's say that theta 1 equals to 0, then it's parallel to each other.
In one direction, then I have only this, right? Theta 2 plus theta 3 has to be 0. Then it's n equal to supersymmetric theory. Then states I would get from these branes that would be n equal to supermultiplets, because they would intersect only, in the second and third, locally described R2, right? Yeah. Yeah.
Can you do this flavor by this per se?
Flavor?
All colors, right?
Well, that's not, one is A, one is B, right?
But you have some open string excitation with both of them. I mean, you can introduce kind of properly to introduce flavor.
By flavor, you mean whether it's what? So in particular, you see if this A is U3 color, and this B is U2 left, okay, of the standard model. Those are gate symmetries of the standard model, let's say. Then this would be left-handed quarks, because they would be 3 under U3 and 2 under U2. But this is what I'm saying. Oh, this is here. So family replication. This is the third thing, which was the first part of my lecture, but I didn't want to tell you. This is replication of families. The first part of my lecture was calculating intersection of cycles.
What if you add
Yeah, this was the whole point of the first. Yeah, but you see, the point is, I did first thing. Why did I do that? To convince you there are a finite number of intersections, right? And it's topological. But I didn't tell you what states are localized at those intersections, right? Because that was this highly involved, right, analysis of quantizing strings at intersections.
Yes, the people just introduce properly to, introduce flavor like a Cauchy coach. If this
That's different.
No, yeah. So the family replication is number of intersections, right? Okay. Now, if you want some flavor symmetry, that comes in the couplings, right? Different families, different intersections. Okay. Different intersections, different Yukawa couplings. Okay. So maybe I'll sketch some things about the coupling. So flavor symmetry in this family replication is encoding in the nature of Yukawa couplings. Yeah. Okay.
Why don't we get to the complex conjugate representation?
Then I just take the strings going the other way around.
So we do get complex conjugate.
Yeah, they are always complex conjugate fields.
So
Okay.
in what sense is it a chiral matter?
Well, in each theory, as a physical multiplet, it's single multiplet, right? It's complex conjugate is also a state, right? But it's a different thing, right?
I thought you need to be in the complex gauge representations to get a chiral matter.
Complex.
Confusion here between first quantization and second quantization. This is the string theory counting is first quantization counting the particle states. So the other one is the antiparticle.
Right.
In terms of that appears in the same field. So there's one chiral field.
Yeah. Thank you. Okay, yeah. Okay, maybe we can chat more, okay?
Yeah, I just have one.
Yes,
question.
please. Yeah.
So,
Yeah.
I mean, whatever we have derived, we're still on the D6 world volume.